Okay, the last is the design of the pressure vessel, which is subjected to the combined load. Okay, the combined load is the addition to the internal pressure, which include the other loads such as pressure, weight of the vessel and its content, wind load, earthquake, and external load imposed by piping and attached equipment. Okay, referring to the previous topic that we have learned in design the pressure vessel, the considerations should taken into account on the weight load as well. So the load basically the list of the load here are referred to the main load, not the subsidiary load. Okay, this is necessary to determine the resultant stress in the vessel due to the combined load after the thickness at shell is obtained. Okay, the first is the pressure. Okay, the pressure is related to the stress, which the stress can be categorized into primary and secondary. Okay, the primary stress are the stress which is necessary to satisfy the condition of static equilibrium. Okay, if they exceed the yield point of the vessel, of the material, the gross distortion, and in the extreme condition, the failure of the vessel will occur. But for the secondary stress, which is related to the stress that arises from the constraint of adjacent parts of the vessel. It is a self-limiting and has a local yielding or slight distortion will satisfy the condition causing the stress, and failure will not be expected to occur in one application of the loading. So to conduct the resultant set, we may focus more on the primary stress. Okay, the primary stress can be divided into a few parts. Okay, first is the longitudinal or denotes by sigma H, and circumferential stress which denoted by sigma L. Okay, these both stress are due to the pressure regardless of any type of the pressure including internal and external. Okay, these are the equation to measure the longitudinal and circumferential stresses. So we consider the design pressure, internal diameter, and also the thickness on the at the shell. Okay, so these are the schematic diagram for longitudinal and circumferential stress. So you can see here for longitudinal, it has this opposite direction to the force here. And for the circumferential, so we have to consider on the pressure vessel. The next is the direct stress, or denoted by alpha, or denoted by the sigma W. Okay, the direct stress is due to weight of the vessel, including its content and any attachment on the vessel. Okay, the stress can be determined using this equation, which is WZ is the total weight, and the DI is internal diameter, and T is the thickness. So you can see here, okay, the direct stress either can be tension or due to the compression. So the difference is the symbol here. For the compression, we have minus, and for the tension, we have the positive value of the direct stress. And we also consider the support here. So this is related to the shear stress, or that can be explained later. Okay, next is the bending stress. A bending stress resulting for the bending moment to which the vessel is subjected. Okay, it includes the total weight of vessel and its content for horizontal pressure vessel, and wind load and seismic load in case of vertical pressure vessel. Okay, the equation is involved the bending moment at the plane being considered. LV is the second moment of area of the vessel about the plane, and you may use this equation to determine the second moment of the area. We have also considered the internal diameter and also the thickness. Okay, the last is the torsional shear stress, or denoted by tau. Okay, resulting for the torque caused by the load offset from the vessel axis. And the stress can be determined using this equation. Somehow we can neglect the torque applied on the vessel as well. Okay, so T is the torque, and IP is the polar sector moment area that you can determine using this equation. Okay, the principal stress is defined as the maximum value of the normal stresses at the point which at on the plane or on which the shear stress is zero, which is acting on the point wall on the vessel. So we have the first principal stress, secondary principal stress, and also third principal stress. However, the most study applied the first and also the secondary stress, which the third principal stress usually negligible for the wall vessel. Okay, sigma z is the total longitudinal stress, which include the longitudinal, the direct stress, and also the bending stress. Okay, the direct stress should be counted as positive if tension and negative if compression. So the top or the top stress is not usually significant related to the principal stress. Okay, to check on the safety of the cylindrical vessel shell, we may refer to this start. First, we can perform the safety or design check on the pressure vessel based on the wall thickness, which the thickness should less than the maximum allowable stress. That means we have the design is safe or the pressure vessel is safe to be proceed. And second, the criteria is based on the allowable stress intensity. We may determine the allowable stress intensity using this equation. So basically it should less than the maximum allowable stress. So the first principal stress minus the secondary principal stress, or if you neglect the third principal stress, you may neglect this part. Okay, the third criteria is based on the compressive stress and elastic stability, which is related to the external pressure. So we can determine the critical buckling stress using this equation. RP is the radius of curvature, and we have this equation as well. Okay, for the steel at ambient temperature, this is the value of Young modulus. So basically, the maximum value of the resultant stress or the sigma z should be less than the critical buckling stress. Okay, the next is the weight load. Weight load include the vessel shell, the vessel fitting such as main, waist, and nozzle. We have internal fitting such as plate plus the fluid on the plate. So you should consider the fluid on the plate as well, heating and cooling coil. And then next we have the external fitting such as ladder, platform, and piping. And we have the auxiliary equipment which is not such a support such as condenser and agitator that mounted or connected to the pressure vessel. So insulation also can consider as weight load. So such as on the reactor that we need to maintain the temperature on the reactor. So you may consider to install the installation or culvert surrounding the pressure vessel. And then we have the weight of the liquid to fill the vessel, basically the vessel content. Okay, the vessel will be filled with the water for the hydrostatic pressure test, and it may fill with the process liquid due to the mist operation. So to conduct the hydraulic pressure test, after we calculate the design pressure, the pressure vessel will be inserted with the water before we can conduct the hydraulic pressure test, which is based on the design pressure, whether to check and to evaluate the pressure vessel, whether it can withstand with the certain range of the pressure or based on the design pressure. Okay, for the weight load, okay, we can determine it using this equation, which is approximate weight of the cylindrical vessel with dome and uniform wall thickness can be estimated using this equation. So we consider the factor to account, which 1.08 for the vessel with only few internal fitting, or if we design the distillation column which have several main weight and also the plate support and equivalent fitting, you can use this value. Okay, it also include the height or the length between tangent lines and the length of the cylindrical section, So include the wall thickness, the density or the vessel material. So you may refer to the reference book. What is the density for this particular design material, such as for the stainless steel, carbon steel. It has own design or the density. And then we also consider the mean diameter for the vessel, which you can use this equation or by consider the additional thickness or the thickness on the vessel. Okay, for the steel vessel, this equation can be simplified into this equation. Okay, the third is the wind loads, okay, related to the tall vessel. Basically, for the economic design purposes, the plate thickness at the base should be higher than at the top. Example, if we have the tall vessel here, so maybe we divide it into a few sections, okay, 5 sections. So basically the thickness on the base is a much higher compared than the at the top. Okay, this is due to the economic design purposes. Okay, the thickness at the top being sufficient for the pressure load and that at the base is sufficient for the pressure plus the maximum bending moment. So we consider the maximum bending moment here. So this is the load per length or per the unit length. And this is the distance measure from the free end. So this is we consider as and also the wind load here. Okay, for the bending moment at a column base, so at the column base here, we can use this equation. FP is the local concentrated load, and also HP is the height of the concentrated load above the column base. Okay, continue for the wind load. Okay, this is how we can determine the wind pressure using this equation, or we can use this equation also. So basically, it based on the wind velocity. We can start the preliminary design using this wind speed, or it turns to the wind pressure equal to 1,280 Newton per meter square. Okay, to determine the loading, which is per line meter, the pressure or wind pressure times the effective column diameter, which is the outside diameter plus an allowance for the thermal insulation and attachment. So example, if we have the column here, so it include the insulation here, and also the any attachment, maybe it attached with other auxiliary other auxiliary instrument as well. So we include the attachment as well to determine the loading of per linear meter. Okay, the next is earthquake loading. So the movement of the earth's surface during an earthquake produces horizontal shear force on top the self-support vessel, and the magnitude of which increase from the base upward. So we can determine the total shear force using this equation. WV is the total weight of the vessel including its content, and AEG is the seismic constant of denoted by CE. You may also refer to the reference book, the constant value here. And then we have external load. Okay, for the auxiliary equipment attached to the tall vessel, we can determine the bending moment, which is including the auxiliary equipment that attached to this column. Okay, usually it related to the tall vessel as well, which we subject to the vessel to a bending moment if the center of the gravity of the equipment does not coincide with the center line of the vessel. So we consider the weight of the equipment and also the distance between the center. So this is LON, weight on the equipment, and we can determine the bending moment. So this is the overall for the combined load.